In this video, I'd like to tell you a bit about the math behind large margin classification. This video is optional, so please feel free to skip it, but it may also give you better intuition about how the optimization problem of the support vector machine, how that leads to large margin classifiers. In order to get started, let me first remind you of a couple properties of what vector inner products look like. Let's say I have two vectors u and v that look like this, so both two-dimensional vectors. Then let's see what u transpose v looks like. And u transpose v is also called the inner product between the vectors u and v. U is a two-dimensional vector, so I can plot it on this figure. So let's say that's the vector u. And what I mean by that is if on the horizontal axis, that value takes whatever value u1 is, and on the vertical axis, the height of that is whatever u2 is, the second component of the vector u. Now, one quantity that would be nice to have is the norm of the vector u. So these are double bars on the left and right that denotes the norm or the length of u. So this just means really the Euclidean length of the vector u, and this, by Pythagoras theorem, is just equal to u1 squared plus u2 squared square root, right? And this is the length of the vector u. That's a real number. It just says, what is the length of this? What is the length of this vector down here? What is the length of this arrow that I just drew is the norm of u. Now, let's go back and look at the vector v, because we want to compute the inner product. So v will be some other vector with some value v1, v2, and so the vector v will look like that. So we're going to draw v like so. Now, let's go back and look at how to compute the inner product between u and v. Here's how you can do it. We're going to take the vector v and project it down onto the vector u. So I'm going to take a orthogonal projection, or a 90-degree projection, so project it down onto u like so. And what I'm going to do is measure the length of this red line that I just drew here. So I'm going to call the length of that red line p. So p is the length, or is the magnitude, of the projection of the vector v onto the vector u. Right? So let me just write that down. So p is the length of the projection of the vector v onto the vector u. And it's possible to show that the inner product u transpose v, that this is going to be equal to p times the norm, or the length, of the vector u. So this is one way to compute the inner product, and if you actually do the geometry and figure out what p is and figure out what the norm of u is, this should give you the same answer as the other way of computing the inner product, right? Which is if you take u transpose v, then u transpose is this u1, u2 is a 1 by 2 matrix, and then times v, and so this should actually give you u1 v1 plus u2 v2. And it's sort of a theorem of linear algebra that these two formulas give you the same answer. And by the way, u transpose v is also equal to v transpose u. So if you were to do the same process in reverse, instead of projecting v onto u, you could project u onto v, then do the same process but with the rows of u and v reversed, and you should actually get the same number, whatever that number is. And just to clarify what's going on in this equation, the norm of u is a real number, and p is also a real number, and so u transpose v is the regular multiplication of two real numbers of the length of p times the norm of u. Just one last detail, which is if you look at the norm of p, p is actually signed, so right, and it can be either positive or negative. So let me say what I mean by that. If u is a vector that looks like this, and if v is a vector that looks like this, so if the angle between u and v is greater than 90 degrees, then if I project v onto u, what I'll get is a projection that looks like this. And so I'm going to have that length P. And in this case, I will still have that U transpose V is equal to P times the norm of U, except that in this example, P will be negative. So, in inner products, if the angle between U and V is less than 90 degrees, then P is the positive length of that red line. Whereas if the angle, if this angle here is greater than 90 degrees, then P here will be negative of the length of this little line, of that little line segment over there. And so the inner product between two vectors can also be negative if the angle between them is greater than 90 degrees. So that's how vector inner products work. We're going to use these properties of vector inner product to try to understand the support vector machine optimization objective a little better. Here's the optimization objective for the support vector machine that we worked out earlier. Just for the purpose of this slide, I'm going to make one simplification, just to make the objective easy to analyze. And what I'm going to do is ignore the intercept terms. We'll just ignore theta 0 and set that to be equal to 0. To make things easy to plot, I'm also going to set n, the number of features, to be equal to 2. So we have only two features, x1 and x2. Now let's look at the objective function, the optimization objective of the SVM. When we have only two features, when n is equal to 2, this can be written 1/2 of theta 1 squared plus theta 2 squared, because we only have two parameters, theta 1 and theta 2. And what I'm going to do is rewrite this a bit. I'm going to write this as 1/2 of theta 1 squared plus theta 2 squared, and then square root squared. And the reason I can do that is because for any number, w, right, the square roots of w and then squared, that's just equal to w. So square roots and squared should give me the same thing. And what you may notice is that this term inside the parentheses, that's equal to the norm or the length of the vector theta. And what I mean by that is that if we write out the vector theta like this, that's theta 1, theta 2, then this term that I've just underlined in red, that's exactly the length or the norm of the vector theta, following the definition of the norm of a vector that we had on the previous slide. And in fact, this is actually equal to the length of the vector theta, whether we write it as theta 0, theta 1, theta 2, that is if theta 0 is equal to 0, as I assume here, or just the length of theta 1, theta 2. But for this line, I'm going to ignore theta 0. So let me just treat theta as this, let me just write theta, the norm of theta, as this theta 1, theta 2 only. But the math works out either way, whether we include theta 0 here or not. So it's not going to matter for the rest of our derivation. And so finally, this means that my optimization objective is equal to 1/2 of the norm of theta squared. So all the support vector machine is doing in the optimization objective is minimizing the squared norm or the squared length of the parameter vector theta. Now what I'd like to do is look at these terms, theta transpose x, and understand better what they're doing. So given a parameter vector theta and given an example x, what is this equal to? And on the previous slide, we figured out what U transpose V looks like for different vectors U and V, and so we're going to take those definitions, with theta and xi playing the roles of U and V, and let's see what that picture looks like. So let's say I look at just a single training example. Let's say I have a positive example that drawing is across there, and let's say that's my example xi, right? So what that really means is that I've plotted on the horizontal axis some value xi1 and on the vertical axis xi2. That's how I plot my training examples. And although we haven't been really thinking of this as a vector, what this really is, this is a vector from the origin, from 0, 0, out to the location of this training example. And now, let's say we have a parameter vector theta, and I'm going to plot that as a vector as well. And what I mean by that is I'm going to plot theta 1 here and theta 2 there. So what is the inner product theta transpose xi. Well, using our earlier method, the way we compute that is we take my example and project it onto my parameter vector theta, and then I'm going to look at the length of this segment I'm coloring in red, and I'm going to call that P superscript I to denote that this is a projection of the ith training example onto the parameter vector theta. And so what we have is that theta transpose xi is equal to, following what we had on the previous slide, this is going to be equal to P times the length or the norm of the vector theta. And this is of course also equal to theta 1 x1 plus theta 2 x2. So each of these, is an equally valid way of computing the inner product between theta and xi. Okay, so where does this leave us? What this means is that these constraints, that theta transpose xi be greater than or equal to 1, or there's less than or equal to minus 1, what this means is I can replace these with constraints that pi times x be greater than or equal to 1, because theta transpose xi is equal to pi times the norm of theta. So writing that into our optimization objective, this is what we get, where I have, instead of theta transpose xi, I now have this pi times the norm of theta. And just to remind you, we worked out earlier too that this optimization objective, that can be written as 1/2 times the norm of theta squared. So now let's consider the training example that we have at the bottom. And for now, continuing to use the simplification that theta 0 is equal to 0, let's see what decision boundary the support vector machine will choose. Here's one option. Let's say the support vector machine were to choose this decision boundary. This is not a very good choice because it has very small margin. This decision boundary comes very close to the training examples. Let's see why the support vector machine will not do this. For this choice of parameters, it's possible to show that the parameter vector theta is actually at 90 degrees to the decision boundary. And so that green decision boundary corresponds to a parameter vector theta that points in that direction. And by the way, the simplification that theta 0 equals 0, that just means that the decision boundary has to pass through the origin 0, 0 over there. So now let's look at what this implies for the optimization objective. Let's say that this example here, let's say that's my first example, x1. If we look at the projection of this example onto my parameters theta, that's the projection. And so that little line red segment, that is equal to P1. And that's going to be pretty small, right? And similarly, if this example here, if this happens to be x2, that's my second example, then if I look at the projection of this example onto theta, then let me draw this one in magenta. This little magenta line segment, that's going to be P2. That's the projection of the second example onto the direction of my parameter vector theta, which goes like this. And so this little projection line segment is going to be pretty small. P2 will actually be a negative number, right? So P2 will be because it's in the opposite direction. This vector has greater than 90-degree angle with my parameter vector theta, it's going to be less than 0. And so what we're finding is that these terms pi and are going to be pretty small numbers. And so if we look at the optimization objective and see, well, for positive examples, we need pi times the norm of theta to be bigger than or equal to 1. But if pi over here, if p1 over here is pretty small, that means that we need the norm of theta to be pretty large, right? Because if p1 of theta is small and we want p1 times the norm of theta to be bigger than or equal to 1, well, the only way for that to be true, for the product of these two numbers to be large, if p1 is small, is if we set norm of theta to be large. And similarly, for our negative example, we need p2 times the norm of theta to be less than or equal to minus 1. And we saw in this example, right, that P2 is going to be a pretty small negative number. And so the only way for that to happen as well is for the norm of theta to be large. But what we're doing in the optimization objective is we're trying to find a setting of parameters where the norm of theta is small. And so, this doesn't seem like such a good direction for the parameter vector theta. In contrast, let's look at a different decision boundary. Here, let's say this SVM chooses that decision boundary. Now the picture is going to be very different. If that's the decision boundary, here's the corresponding direction for theta. So with the decision boundary, being that vertical line, that corresponds to, it's possible to show using linear algebra that the way to get that green decision boundary is to have the vector theta be at 90 degrees to it. And now, if you look at the projection of your data onto the vector x, let's say as before that this example is my example x1. So when I project this onto x, onto theta, what I find is that this is P1, that length there is P1, and from other example, if that example is x2, and I do the same projection, then what I find is that this length here is P2. Really, this is going to be less than 0. And you notice that now P1, right, and P2, these lengths of the projections are going to be much bigger. And so if we still need to enforce these constraints that P1 of the norm of theta is greater than or equal to 1, because P1 is so much bigger now, the norm of theta can be smaller. And so what this means is that by choosing the decision boundary shown on the right instead of on the left, the SVM can make the norm of the parameters theta much smaller. So it can make the norm of theta smaller and therefore make the squared norm of theta smaller, which is why the SVM would choose this hypothesis on the right instead. And this is how the SVM gives rise to this large margin classification effect. Namely, if you look at this green line, if you look at this green hypothesis, we want the projections of my positive and negative examples onto theta to be large, and the only way for that to hold true is if, surrounding this green line, there's this large margin, there's this large gap that separates the positive and negative examples, and there's really the magnitude of this gap, the magnitude of this margin is exactly the values of P1, P2, P3, and so on. And so is by making the margin large, or by making these terms P1, P2, P3, and so on, that the SVM can end up with a smaller value for the norm of theta, which is what it's trying to do in the objective. And this is why the support vector machine ends up with a large margin classifier, is because it's trying to maximize the norm of these PIs, which is the distance from the training examples to your decision boundary. Finally, we did this whole derivation using this simplification that the parameter theta 0 must be equal to 0. The effect of that, as I mentioned briefly, is that if theta 0 is equal to 0, what that means is that we're entertaining only decision boundaries that pass through the origin, so decision boundaries that pass through the origin like that. If you allow theta 0 to be non-zero, then what that means is that you entertain decision boundaries that do not pass through the origin, like that one that I just drew. And I'm not going to do the full derivation, but it turns out that the same large margin proof works pretty much in exactly the same way. And there's a generalization of this argument that we just went through, that I'm not going to go through, that shows that even when theta 0 is non-zero, what the SVM is trying to do when you have this optimization objective, which again corresponds to the case of when C is very large. But it's possible to show that even when theta 0 is not equal to 0, the support vector machine is really trying to find a large margin separator between the positive and the negative examples. So that explains how the support vector machine is a large margin classifier. In the next video, we'll start to talk about how to take some of these SVM ideas and start to apply them to building complex nonlinear classifiers as well.